Welcome to this video lecture. This is Mark Scythian, FAA licensed aerospace technician, airframe, power plant, and avionics certified. The date today is July 8, 2016. In this video lecture, we're going to cover the very basics of propulsion, aerodynamic lift, and propellers. This really sets the basic framework for understanding the overall concept of how wing lift and propeller thrust and propulsion in general work. And they're all really connected to each other. They're just set up differently between linear and angular flow. And then, anytime you accelerate any type of mass, including the air, you're going to get thrust or a reactionary force. So I'll start with a lecture that I put together here and just cover the very basics so the idea is understood and people who seek to learn more can build up on the basics. Propulsion operates on the principle of acceleration of mass airflow in order to cause a forced action in the direction of the mass airflow acceleration so that a reactionary force in equal and opposite direction takes place, known as thrust. Force is mass times acceleration. If you're using the metric system, you can just simply take the kilograms per second mass airflow and multiply it times the final speed of the jet velocity minus the starting speed, and then the time it takes to make that acceleration, so say 1 second. So it becomes a acceleration component, meters per second squared, and that's it. You'll end up with a Newton's force. There's 4.45 newtons to 1 pound of force. But if you're using the US units of measure, you can take the pounds per second mass airflow times the final speed of the jet velocity and then simply divide it into gravitational acceleration, and you'll get the pounds force thrust. The density of the air near sea level and 59 degree Fahrenheit air temperature is approximately 0.074 pounds per cubic foot. There, in other videos, I have the atmospheric pressure formula and the air density formula. You use them together, and then you can accurately calculate the density of the air at any elevation up to 36,089 feet and any temperature range in the Fahrenheit scale. But this is approximately what you have for the density of the air, the weight by the given amount of volume. So it's about 13.5 cubic feet of air is 1 pound by weight. So when that air is distributed out over so much surface area, it becomes what we call atmospheric pressure. That's the weight of the air distributed over the surface of the earth. So the higher you go, the atmospheric pressure drops, right? So fluids are both gases and liquids. Air and water are fluids and take the shape of a solid structure they make contact with. Fluids readily exert static pressure on whatever they make contact with. The pressure of the mass air of the atmosphere upon the Earth's surface is known as atmospheric pressure. Pressure is force divided by area. When occupying space within the Earth's atmosphere at sea level, it is similar to existing at the bottom of the quote-unquote bottom of the ocean of air. Now, in terms of aerodynamic wing lift, the whole concept of airfoils and wing lift is actually quite simple. It relies on the principle of differential speeds of the air to cause lift. So at the top of the wing, the air will move faster than the airflow at the bottom of the wing due to the curve at the top of the wing. When the airflow splits as it makes contact with the front of the wing leading edge, the curve at the top of the wing makes the travel of the airflow longer compared to the bottom of the wing. The speed of the air will accelerate faster at the top of the wing compared to the bottom of the wing. When a fluid such as air moves faster than the relative air around it, it will have a pressure below atmospheric pressure. So atmospheric pressure takes the place of the vacuum at the bottom of the wing. Pressure is force is pressure times area. This is the Bernoulli's component of wing lift, which makes up around 40% of the wing lift. But more importantly, Bernoulli's lift component keeps the air on the wing as if it is an elastic wrapping known as the boundary layer. Once enough airflow speed envelops the wing's airfoil, then changing the angle of the wing by means of flight control surfaces, such as the elevator at the rear of the airplane moving up, will cause the tail to move down, causing the nose of the airplane to move up, changing the angle of the wing's airfoil profile to a positive angle. This further slows down the air at the bottom of the wing and further increases the airflow speed at the top of the wing, allowing force lift in the form of mass times acceleration to add to The second component of aerodynamic wing lift, also known as the Newtonian lift component. So you have both the Bernoulli and the Newtonian lift component. Bernoulli is getting force through pressure, and the Newtonian is getting force by acceleration of mass air. As for that force representing the thrust, or the lift, that's what you're getting out of it. So as you can see, there's two different vectors that come out. One for pressure lift this way, and one for mass acceleration that way, so the resultant is a lift kind of in between that. That's just the vector sum. As for propellers, they are no different than rotating wings, for which the angle is higher at the root of the blade and lower at the tip of the blade. That is because the actual angular speed at the root of the propeller is a function of the circumference. Since the circumference is lower at the root of the propeller blade, the actual airflow and circumferential travel is much lower at the root of the blade compared to the tip of the blade. The tip of the blade is where the angular speed and circumference is the greatest, and therefore the most airflow speed takes place, so hence a lower angle at the blade tip. This is known as propeller helical twist, set at a certain structural degree. This allows for consistent amount of lift across the entire propeller blade so that it behaves as if it is a rotating wing, which is what the propeller actually is. But instead of having to travel in linear manner forward, the airflow over the propeller blade's rotating wings develops its airflow by rotation of the propeller blades in the same exact Bernoulli and Newtonian lift and thrust force components that apply to fixed wing airfoils. Rotating wing airfoils are also known as propellers. Now, a column of air makes up the propeller disc area when the propeller blades are rotating, and this column of air is what is accelerated, allowing propellers to develop thrust, and propeller blades are partly developing lift or thrust in the form of bending force by means of pressure differential between the upper and lower airfoil surfaces of the propeller blade. This is represented by the Bernoulli force component. After enough airflow speed develops over the propeller blades, then their angle from the helical twist permits the Newtonian force component, just as fixed-wing airfoils rotate their wing angle during takeoff, to take advantage of the Newtonian lift force component after the Bernoulli's lift force component provides for a stable airflow boundary layer over the wing airfoil structure. So if we look at the propeller from the front view, that would be the column of air being accelerated in an open atmosphere. As for propeller capabilities, the helical twist is only structurally fixed for keeping the coefficient of lift constant through the span of the propeller blade, or through the propeller blade span. But what is relevant to the propellers is the pitch value. The pitch represents the amount of airflow displacement the propeller will induce per every rotation of the propeller. So if a propeller has a pitch of 12, which is 12 inches, and a 1 foot diameter, this means every time the propeller makes one revolution, it is designed to displace 12 inches of airflow through that so-called column of propeller disc area. Propellers themselves are extremely complex in their finite elemental analysis, and their performance dynamics vary from manufacturer to manufacturer. But the most important data regarding propellers are the pitch, the diameter, the RPM, number of blades, air density, and percent propeller efficiency. There's a logarithmic increase in thrust and drag in regards to multi-blade, more than 2-blade propellers, and finding the correct formulation for the given propeller type is key. Percent propeller efficiency is the ratio between the amount of shaft horsepower delivered to the propeller by an engine and its equivalent propeller thrust output by the rotation of the rotating airfoil blades. Typically, propellers tend to operate 80% propeller efficiency. The basic and simplified formula for calculating the approximate static and net thrust output of a propeller is by using the simplified momentum theory. This is simply taking the disk area of the propeller when the blades are rotating and finding out the area, then multiplying the revolutions per second times the pitch, and then converting that into pounds per second mass airflow from the cubic feet per second mass airflow discharge out of the propeller. That would be the disk area of the propeller times the speed at which the airflow is discharged out of the propeller. So 2 dimensions times a third, you get the cubic feet per second mass airflow, and then you can multiply that times the air density to get the pounds weight of air being accelerated. This is similar to jet propulsion, but is limited by slower airflow acceleration and limits to frontal drag based on blade pitch. The aerodynamic wing lift of an airplane wing is based on the coefficient of lift for the given airfoil, certified by manufacturers, times the 2D wing area times the air density in slugs per cubic foot, which is the pounds per cubic foot density multiplied times 0.031, then times the airspeed over the wing airfoil in feet per second. This value multiplied times itself or squared, then this value divided by 2. The simplified momentum theory for propeller thrust, simply half the air density in pounds per cubic foot times the disk area in square feet times the propeller discharge speed in feet per second quantity squared minus the oncoming airflow if the aircraft is moving in feet per second, and that quantity squared, the difference between it. That's just an approximate value for the propeller thrust. Propellers are best experimentally tested for their static thrust, relying on manufacturing. Propellers are best experimentally tested for their static thrust, relying on manufacturers. Got a lot of typos here. Manufacturers' specifications for mass airflow ratings to understand the performance output of each given propeller. Or manufacturer software programs for the given propeller must be accessed to know the performance limits of any given propeller. The details behind how propellers generate thrust are extremely complicated, involving also multi-blade applications which substantially change thrust drag and flight speed limitations, not to mention variable blade pitch applications for constant speed propellers. Constant speed propellers, opposed to fixed pitch, change their pitch angle to keep the propeller RPM constant. The simplified momentum theory for propeller thrust just gives an approximate value for a propeller's net and static thrust output. Now, as for aerodynamic wing lift for fixed wing airplanes, this can be calculated by the following formula. You simply take the coefficient of lift for the given airfoil times the air density in slugs per cubic foot times the wing 2D planform area in square feet times the airflow over the wing, that in feet per second, and the entire quantity then squared. These 4 values then divided by 2. This must be tied to the lift to drag ratio L/D specification for the airfoil, and likewise, conversely, there is aerodynamic drag, and that is the same as the aerodynamic lift formula, except you replace the coefficient of drag for the airfoil or the airplane, or the entire total drag coefficient for the entire airframe and power plant, including the propeller, times the air density in slugs per cubic foot times the projected frontal area of the wing. That is different because when the wing takes an angle, it's going to project the lower surface as projected frontal area, but you have to look at the airfoil angle, critical angle map or the chart. So you got to figure that out by the angle, and then that will get you the projected frontal area. You can figure that out 10 times the airspeed over the wing in feet per second quantity squared, and then the entire quantity divided by 2, and then you divide the lift over the drag, but that should be tied to the lift to drag ratio given for the airfoil. So for every so many pounds of lift, it'll tell you how many pounds of drag. It'll give you that ratio coefficient, so when you're doing these calculations, you can pretty much figure out what's going on, especially if you're on the pilot or technician level. The engineers that design the wing airfoil publish all the specifications, and you can go from them. But this is just the basic formulation to interpret it. Both the lift and drag coefficients are tied to the wing angle, since at higher angle the projected frontal area also includes the bottom of the wing becoming projected frontal area. All airfoil specifications, including the critical angle limit for how much the wing can be angled before flow separation occurs, and these angle limits must be observed by the operators, the pilots, maintained by the technicians, in order for safe flight operations. The specifications for any certified airfoil are listed by the aeronautical engineers that publish them for the given airfoil, and then the pilots and technicians can abide by them for correct aircraft functionality and operation. Lastly, the L/D is simply the aerodynamic lift over the aerodynamic drag. at the given angle. Now, if the L over D is already published, then you're pretty much going to have an easy time getting the lift and the drag at a certain angle based off the coefficient of lift at the angle. So at the given angle, the airfoil map or graph for which the coefficients are tied to, that is because these two formulas are calculating lift and drag at a given wing angle in a ratio relative to the oncoming airflow for which a certain lift coefficient and drag coefficient exist. Their ratio is what establishes the limitations. The last part of this lecture reminds one of the concept of what jet propulsion actually is. It is nothing more than the acceleration of mass airflow in a controlled manner. As we can see here, the total airflow through the jet propulsion engine is the ms, the pounds per second mass airflow. Oncoming airflow during flight is the V1 in feet per second. Jet velocity out of fan core, the cold and hot gas ducts on this turbofan is the V2 in feet per second. And then the G is the gravitational acceleration at 32.2 feet per second squared. And so if you just want the static thrust output when the engine's not moving, you just take the mass airflow times the jet velocity, mass airflow in pounds per second times jet velocity in feet per second, and divide it by gravity. And then if you want to know the thrust when the engine is moving, you simply take the mass airflow through the engine in pounds per second, multiply it times the difference between the jet velocity and the oncoming airflow in feet per second. Then you multiply these two out and divide it by gravity. So that's the basics of propulsion, aerodynamic lift, and propellers. Thanks for watching this video and have a great day.